Hello Gators, this is 5.2 Extreme Value Theorem, Global versus Local, Extrema, and Critical Points. 5.3 Determining intervals on which a function is increasing or decreasing. The extreme value theorem says this: if a function f is continuous over the closed interval a to b, then f has at least one minimum value and at least one maximum value on the closed interval. Now this picture is not continuous, but we can still talk about these words. Global is another word for absolute. I'll probably be using the word absolute, but just in case the AP test uses global, you'll know that's the same thing. Local extrema is the same thing as relative extrema, and that's what I'll be using, relative extrema. So let's take a look at this. This point right here is the lowest y value, so that we call this the absolute min. This y value right here is the highest y value in the interval. We call this an absolute max. This value right here, we call it an absolute min, and that's because if we were to go right down here and look at the values before and afterwards, we would find that this would be the lowest value. Not the lowest value in the whole interval, but it is a relative min. It's the smallest in the neighborhood. Over here we have a value, and if we were to take this down, we would notice that its value is lower than any of the values in the neighborhood, and so we call that one a relative min. And right over here, this is a relative min because in the neighborhood it's the smallest value, a relative min. And this endpoint, since it doesn't have anything to the right of it, we would call this a relative max. All right, I'm going to do problem 1 and then you will do problem 2. So let's take a look at, start from the beginning right here at x equal to -3, and let's see, it's an endpoint, so we need to say something about it. It's going to be is a absolute min of 1. So here's the x value, here's the y value. Another place we ought to look is right up here at x equal to 0 is an absolute max, and its y value is 5. It looks like we can look at 1, and in the neighborhood it looks like at x equal to 1 is a relative min, smallest value, and it's of 2. Now over here at the endpoint there is no endpoint, so we can't really say what that value is. So I'm going to pause the screencast, see what you can do about answering number 2, and I'll give the answer. And here's the answer. So we can't say anything about the endpoint -3, but we can say something at -1. We can say something at 1, and we can say something at the endpoint 4. Let's find all extreme values and identify the type and where they occur. So what we're going to do is we're going to put a point at our values here. That looks like an absolute max. And over here it looks like we have a relative min. And over here it looks like we have a relative max. And over here we have a relative min, and over here we have a relative max. Notice we do not have an absolute min because the graph keeps going. So let me introduce a vocabulary word called critical point. A point that has a possibility being of an extrema, max, or min. And the reason I have this picture and the definition is I wanted you to see these hills and valleys where curves happen are when we have a derivative equal to 0. So places where the derivative is equal to 0 is a possibility of a hill or valley. Now over here we had a extrema, and that was when the derivative does not exist. So these are places that we can look for critical points. All right, so again, one more time, a point that has the possibility of being an extrema is a critical point, and we look for places where the derivative does not exist or when the derivative is equal to 0. So let's go ahead and do this. This is a cubic, so cubics kind of look like this. And what we're going to do is we're going to find the critical points. So f prime of x, we're going to set it equal, and then this is x squared minus 9. And we're going to look where the derivative does not exist. The derivative exists everywhere, so we're not really looking there. But we do want to look at when f prime of x is equal to 0. When f prime is equal to 0, we're going to set the derivative equal to 0 and go ahead and factor x plus 3 and x minus 3. And we're going to get x is equal to plus or minus 3. And chances are the plus or minus 3 are these places where the cubic is going up and down. Okay, let's take a look at this problem. We want to take a look at when we can find our critical points. Now, before we go any further, let's make sure we understand that x cannot be plus or minus 2. That is not in the domain. So we know we don't have points in that location. So let's go ahead and figure out the derivative. And so we're going to remember that is 4 minus x squared to the 1/2 power. So I'm going to use the power rule. And then this will be 4 minus x squared. I'm going to subtract 1, negative 3/2. And don't forget the chain rule, which is negative 2x. Okay, if this should have been 4 minus x squared to the negative 1/2. And so I forgot to put the negative here when I did the power rule. Everything else looks okay. So when I clean it up a little bit, I am going to have a positive value, and I'll have an x in the numerator, and then I'll have the square root of 4 minus x squared to the 3rd power. Okay, now I know the derivative doesn't exist. G prime does not exist when the denominator is equal to 0. Denominator is equal to 0. So the only time the denominator will be equal to 0 is when 4 minus x squared is equal to 0. That's going to happen when x is equal to plus or minus 2. Well, plus or minus 2 wasn't even in the domain. So I don't really need to consider this because these points will not even be part of my domain. So the next place I want to look at is when the derivative is equal to 0. So g prime equal to 0. The only time a fraction can be equal to 0 is if the numerator is 0. So I'm going to set the numerator equal to 0. And so here's our answer. This is a critical point. X is equal to 0 because that's a guarantee that the derivative will be equal to 0. Okay, let's find the critical points when I give you a graph. And let's decide whether the function is increasing or decreasing. All right, so let's look for critical points. So this will be a critical point, and this will be a critical point, and this will be a critical point. This is a critical point because the derivative is equal to 0, derivative is equal to 0, and the derivative does not exist. I am going to write the number 3 here, give myself a little space, the number 5, give myself a little space, and then the number 6. And so what we're doing is we're considering all the numbers from negative infinity to 3, then we have a 3, and then from 3 to 5, this is the interval from 3 to 5, and then from 5 to 6, and then from 6 to infinity. All right, and we know that this is 0, and this does not exist. And in those intervals that we're looking at, we know that they can only do one thing. And if we look at the curve, we can see that the derivative here is positive, so we know the sign of the derivative is positive. From this interval to here, that looks like it's negative, and then from here to here, that's positive, and then here it's negative. So when is the slope of the function positive? And we know that's when it's increasing. So the increasing will happen in this interval from negative infinity to 3 and from 5 to 6 because the derivative is positive. And we say decreasing intervals are 3 to 5 and 6 to infinity, and that's because the derivative is negative. So the sign of the derivative will indicate whether it's increasing or decreasing. Okay, let's go ahead and do another problem. We want to find when it's increasing or decreasing. First step is to find the critical points. So f prime of x will be equal to negative 2x minus 4. Now we know the derivative exists everywhere, so we're really looking at the critical point when the derivative is equal to 0. When the derivative is equal to 0, we're going to set that equal to 0, and we're going to have 2x is equal to negative 4, and so x is equal to negative 2. So we know that we're concerned with x equal to negative 2. That's a spot to look at. We know the derivative is 0. Then we're going to look at values from negative infinity to negative 2 and from negative 2 to infinity. And we know they're going to be the same in those intervals. Now we can take our derivative, f prime of x is equal to negative 2x minus 4, and we know the sign will be the same anywhere. So I think I'll just pick one of the values in the interval. I think I'll pick like negative 3. And when I pick negative 3, that's going to be a positive 6 minus 4. And that what I'm really concerned about is whether it's positive or negative, and the answer is it's positive. And when I'm going to figure out a value in this interval, 0 is a nice value to use. I'm going to use 0, and so this will be negative 4. I'm not concerned about the 4 part, just that it's negative. And so now I know what's happening before the critical point and after the critical point. So I say that it's increasing in the interval from negative infinity to negative 2 because, and the justification is that the derivative is positive. It's decreasing in the interval from negative 2 to infinity, and we have to identify why, and because the derivative is negative. All right, let's take a look at another one, and we're going to find whether it's increasing and decreasing. Same thing, we want to look for critical points first. Now this is a cubic, so we know that the derivative exists everywhere. So we'll take a look at the derivative, and this is going to be x to the second power minus 2x minus 15. We want to look at finding critical points, which means setting the derivative equal to 0. And when I do some factoring, that'll be minus 5 and then x plus 3. So we know the points will be at positive 5 and negative 3. I'm going to go ahead and put a negative 3 here, give myself some space, and then I'm going to put 5 here and then give my space afterwards. So I'm looking at negative infinity to negative 3, and from negative 3 to 5, and from 5 to infinity. And I know that things are going to be the same there. These are zeros right here. So I'm going to look at my derivative, which is f prime of x is equal to, I like the factored form, and I'll show you why in a minute here. All right, I'm going to test out a point, and the point I'm going to test out is, I'll say negative 5. And when I put negative 5 in here, I know that in this thing I'm going to have a negative value. And when I put a negative in here, I'm going to have negative 5, I'm going to have a negative value here. So a negative and a negative make a positive. All right, and then I'm going to test out a point inside of this interval. I'm going to test out 0. And when I test out 0 in here, that'll be a negative value. And when I put 0 in here, that'll be a positive value. And a negative times a positive is a negative. And then I'm going to test out a point between 5 and infinity. I'll test out a point like 10, somewhere in the interval. If I put 10 in here, I am going to get a positive value. And if I put 10 in here, I'm going to get another positive value. Positive times positive is positive. So now I can state when it's increasing and decreasing. It's increasing in the interval from negative infinity to negative 3 and 5 to infinity because the derivative is positive, and it's decreasing in the interval from negative 3 to 5 because the derivative is negative. Okay, now let's take a look at looking at a graph, but we've got to be very careful because this isn't the function graph. This is the derivative graph. In fact, it might not be a bad idea for us to take a look at the sign of the derivative here. Notice that the derivative at negative 3 is 0, and notice the derivative at 1 is 0. Remember, derivative, this is already a derivative, and this derivative at negative 3 is 0, and this derivative at 1 is 0. Now, the sign of the derivative before that is going to be positive, and the sign of the derivative is underneath the x-axis, so that's negative, and the sign over here to, oops, I need another 3 here, that is 0, and so that's positive, and then after 3 that will be negative. So these are places that I know the sign of the derivative. So it's increasing from negative infinity to negative 3 and from 1 to 3 because, and the reason is the derivative is positive. It's sitting above the x-axis, and decreasing from negative 3 to 1 and from 3 to infinity because the derivative is negative. So be careful with what the graph is telling you. Okay, so if you want to know if something is increasing and decreasing, you look at the sign of its rate of change. So the rate of change can tell you if the independent variable is increasing or decreasing. This is the independent variable right here. It's in the numerator. So the independent variable with respect to the dependent, which is years. So this is telling us that the students, number of students, is increasing, and it's increasing because the rate of change is positive. Over here, the dependent variable is miles, so miles is decreasing. How do I know it's decreasing? Because the rate of change is negative. If we're talking about mastery checks, that is the dependent variable. So mastery checks is increasing, it's positive, and that's because the rate of change is positive. Now here, be careful with this little square. This is virus cases per month. So let's be careful and understand that this is the dependent variable. It is a rate of change. So viruses cases per month is decreasing because this rate of change that we're looking at is negative. All right, let's look at the last one. The rate of change of fruit flies in a kitchen at T days is modeled by this rate of change, this formula, flies per day. All right, so understand that this function is already a rate of change. The question says, shows that the number of flies is decreasing at time t equal to 3. All right, let's take a look at looking at rate versus R of 3 versus R prime. of 3. If you were looking at R prime of 3, you'd be looking at flies per day per day. And it's only asking us to look at the number of flies is decreasing. So we really are just looking at this function. We're putting the number in to see what its value is, or its sign is, and it's negative. So we say that it's decreasing because the rate of change is less than 0. And that's the end of the screencast.